There are other ways that nodes can keep track of their children. So let's reflect just for a moment on our current approach, where we use a data index character map. Effectively, each node stores 128 links. This is the box and pointer version, very small, and here's the cartoon version. And the downside of this is that for typical applications, most of these links will be null. So an alternate picture of this is as follows. Here is a hypothetical abstract trie. We have a root, two children A and C, and A has a child D. And this set corresponds to the keys add and the key C. So in terms of the actual memory boxes needed to keep track of this very simple tree on the left, we have a root node where the key is false, right? The root's always false. It's never the end of a key. And then we have 128 links, only 2 of which are used, link A and link C. So we go to node A. It's not a key in the sense that it is not the final letter in a key. And it has 128 links, only 1 of which is used. This node corresponding to the letter D, it is a key. It's the end of a key, so it's add. And this has 128 links, none of which are used. So we have tons and tons of memory boxes that are just basically going completely to waste. And fundamentally, the problem is that our arrays are very sparse. They are mostly null. Now we could use any other kind of map from character to node. Like we could use a binary search tree instead of this array. Or we could use a hash table. And so let's see what that hash table approach might look like. Oops. So in this approach, we again have a node which has a key boolean and a set of links. Now if it was a hash table, it might look like this. So here's a hash table that has 4 buckets. It has bucket 1 and bucket 3, which contain 1 item each, and the other 2 buckets are empty. So now we are using way less memory. Instead of 128 links, we have only 4 that are buckets, and then we have a couple of little hash table separate chaining nodes here. Okay. So now each of these nodes is itself going to have a key and a value pair. Here the key is a character, of course, and the value is a link to a node in my trie. So for example, the A object here, it will have a value that points at this node that corresponds to the letter A. This one, we're saying it's false because it's this letter here. And it has its own hash table. So this hash table contains only the letter D, and it points off somewhere else. Okay. Now, it might seem a little bit like overkill to have a hash table that has only 1 item in it, but it's actually a pretty good approach. It's better than, in almost all circumstances, better than having just a big array of all possible links. Then on the other side, of course, we have the letter C, which points at a node where the key is true, or where is key is true, and we have a hash table with no items. Okay. What about a binary search tree? What would that look like? Well, in this case, the links would no longer be an array or a hash table, but it would be a binary search tree. And so in this case, this is the most balanced you could possibly have things. We have the letter C and the letter A. And the value in this binary search tree node corresponds to a link to this trie node. So this trie node is the letter A, because it's coming off the link from the letter A. And then we have only 1 link from the letter A, which of course is to D. So this is a trivial binary search tree that has only 1 item. And then on the other side, we have a node which corresponds to the letter C. So it is a key, and currently its tree is empty. Okay? So all of these are perfectly valid ways of building a trie, and so let's think about how we might compare them. Okay? So I want to reiterate this notion that when we have abstraction, like layers of abstraction is a very real and important thing that should be burned into your brain. So for example, when I say I want my next, like my children, it's ultimately a dictionary or a map from letter to node. And there's lots of ways I could do that. I can use a data index character map, a hash table, a balanced binary search tree, or other stuff. So we have to pick some kind of map. And if we compare them, the data index character map idea, it's very fast, but it's memory hungry. The hash table's almost as fast. It's not as fast because we have to compute these hash values and then walk a few links, but it's still going to be quite fast. And then a balanced binary search tree, it's probably going to be a little slower than a hash table on average, but it'll use roughly the same amount of memory. Though I haven't really done a careful analysis, but it'd be pretty close. Let's be just a little more careful about those runtimes and memory usages. So ultimately, using a binary search tree or a hash table will use less memory than a data index character map in almost all circumstances. So in a data index character map, you have 128 links per node, but in a binary search tree, you only have C links per node. That is, if we only have two children, right, like say A and S, we're only going to have 2 nodes in that binary search tree. And so C is the number of children, right? So we're only going to have 2 links, so to speak. Then in a hash table, again, we're going to have C links per node, just like a binary search tree. So our hash table for the root would only have 2 links coming out of it. Now the cost to keep each link is a little higher, because if we look back at our binary search tree, or for example, it's not just the link we have to store, but actually pointers between binary search tree nodes, or in the case of the hash table, we had to store all these buckets. Okay? So these links, there's a little bit of overhead. So it's not just the links that matter, but for the most part, we'll be in better shape for binary search trees and hash tables than we are for the data index character map. So if you count the total number of memory boxes, the binary search tree and the hash table should generally blow the data index character map out of the water. Now this comes at a cost. So even though you're using less memory, using a binary search tree and a hash table means there's a little more work. We have to compute the hash value, we have to iterate through these little short lists, and that's not going to be as fast as just accessing an array. So the data index character map, it's constant time. You're just getting an item out of an array. With a binary search tree, what's going to be big O of log R, where R is the size of the alphabet? Because the biggest possible binary search tree will have depth log R if you're using all possible links. And then the hash table is going to be big O of R. In the worst case, that's if we have some crazy, we shouldn't get a collision, but if somehow all the letters ended up in one single one of our buckets, then you could say it's big O of R. Though in practice, that's never going to happen. But the good news is we don't have to worry too much about these expressions because the alphabet size is fixed. We're not going to change from ASCII to something else. So we can think of all 3 as theta 1. Okay? Now, how much better in terms of the runtime will data index character map be versus binary search trees and hash tables in practice? You'd have to run some kind of experiments. Okay? So, to summarize, when your keys are strings, tries give you better performance on this contains and add operation, or in this case I call it get. Now binary search trees and hash tables will be a little slower, but they'll be much more memory efficient. So there's a little bit of a memory time trade-off, but to me it seems like a clear win to use one of our more advanced ideas than this hyperspeed idea, the data index character map. Okay? Now if you wanted to actually know which is truly better for your application, you'd have to do some kind of computational experiments, but what we'll see is it's actually not this constant time that's so special. So the reason I bothered making this lecture is not, oh, we can go from log time or almost constant time for hash tables to perfectly constant time. What we'll see is that there's special operations that try support that neither hash tables nor binary search trees can easily support. Okay? So we'll be talking about that in the videos to come.